Hello everyone, and welcome to RadioCSIRT English Edition, your daily cybersecurity briefing. I am Marc Frederic Gomez, your French cybersecurity voice covering today's threat landscape. I hope you are doing well. In this episode, Remus, the 64-bit evolution of Lumma Stealer, new infrastructure, new evasion techniques, and an attribution chain that tells us exactly where this threat came from. On April 7, 2026, Gen Threat Labs, the research arm of Gen Digital, published a detailed technical analysis of Remus, a new 64-bit Infostealer attributed to the Lumma Stealer family. Active campaigns involving Remus have been observed since February 2026, which is not a coincidence when you look at the timeline. Between August and October 2025, a doxxing campaign exposed the presumed core members of the Lumma organization, significantly disrupting its operations. Remus emerges in the direct aftermath of that disruption. It is not a replacement for Lumma. Both families are currently coexisting in the wild, but rather a deliberate evolution, most likely born from a fork or a rebranding operation initiated during the period of maximum operational pressure on the original group. Lumma Stealer, also known as Lumma C2, has been marketed as a malware as a service on Russian-speaking forums since at least August 2022. It is attributed to a threat actor operating under the pseudonym Shamel and has established itself as one of the most sophisticated and widely distributed stealers in the current threat landscape, operating on a subscription-based affiliate model with multiple tiers. The standard target profile has not changed with Remus: browser credentials, session cookies, cryptocurrency wallets, clipboard data, and system fingerprint. The attribution case built by Gen Threat Labs is one of the more technically rigorous published in recent months. 6 distinct categories of technical indicators establish codebase continuity between Remus and Lumma. The first is string obfuscation. Both families use a near-identical mechanism: stack assembly of the encrypted string via a series of move instructions, followed by a byte-by-byte decryption loop, reinforced with MBA, or mixed Boolean arithmetic, obfuscation. Each string gets a unique transformation, making a universal static decryptor impractical. Both binaries also insert unusual NOP sequences before decryption loops, a compiler-level artifact consistent with a shared custom-build pipeline. The second and most distinctive attribution indicator is the application-bound encryption bypass for Chromium browsers. Google introduced ABE as a security control to protect browser-stored credentials from being extracted by processes running outside the browser context. Both Lumma and Remus bypass it using an approach not documented elsewhere: injection of a compact shellcode into the browser process to locate the v20_master_ key directly in memory, protected by CryptUnprotectMemory with the CryptUnprotectMemory _same_process flag, then calling CryptUnprotectMemory from within the browser's process context. The difference between the two implementations is a matter of 11 bytes. Remus produces a 51-byte shellcode versus 62 for Lumma through register reuse. Both resolve CryptUnprotectMemory in dpapi.dll via API hashing, a CCRC32 for Remus, FNV-1A for Lumma, and scan the browser module for an opcode pattern pointing to the OS_crypt_async encryptor virtual function table. When no browser process is running, both families launch one on a hidden desktop via create process Lumma using the hard-coded name Chromium dev, Remus using a 16-character alphanumeric string generated by a Mersenne twister PRNG. This level of implementation parallelism, with only minor optimization deltas, is not coincidental. The third indicator is direct syscall usage. Both families bypass the standard Windows API entirely by constructing at runtime a hash-to-SSN lookup table from ntdll.dll exports, routing all system calls through a central dispatcher with a near-identical calling convention. Remus, being a native 64-bit binary, uses the syscall instruction directly. Lumma, which was 32-bit, used sysinter via a fallback chain, including Heaven's Gate for 64-bit browser operations. The architectural shift to 64 bits is one of the documented evolutions in Remus, along with a switch in API hashing from FNV-1A to CRC32 with a custom initialization constant, extended device fingerprinting, a modified exfiltration archive format, and a restructured C2 communication model that delivers configuration incrementally rather than in a single blob. The fourth indicator is the antiVM CPUID check. Both families execute CPUID with EAX set to hexadecimal 40 million, the hypervisor vendor identification leaf, and compare the ECX result against 5 hypervisor signatures in the same order: KVM, QEMU/T, CG, VMware, VirtualBox, and Xen. The fifth is the crypter presence check. Both families display a warning dialog via a direct NtRaiseHardError call when executed without a protective layer, a mechanism rare enough in the malware ecosystem to be a meaningful fingerprint. The sixth is shared control flow obfuscation patterns, clipboard theft routines, PE structure layout, and C2 configuration format, all structurally identical between the two families. The attribution chain is anchored by a transitional build set called Tensor, compiled on the 16th of September 2025, at the peak of the disruption period. Tensor shares with Lumma an identical Steam-Dead drop resolver profile present across multiple confirmed Lumma samples, while already containing artifacts exclusive to Remus, including the ABE bypass wildcard string that serves as a behavioral fingerprint. This dual anchorage makes Tensor the strongest single link in the attribution chain. The most operationally significant evolution in Remus is the abandonment of Steam and Telegram dead drop resolvers in favor of ether hiding. At runtime, Remus sends a JSON-RPCETH_call request to a hard-coded Ethereum smart contract address via a public RPC endpoint and extracts the C2 URL from the hex-encoded response. The decentralized and immutable nature of the blockchain makes this infrastructure effectively resistant to traditional takedown procedures. No platform operator to notify, no domain registration to suspend. This is a meaningful operational upgrade. Steam and Telegram infrastructure can be taken down through abuse reports and platform cooperation. An Ethereum smart contract cannot. The smart contract address itself is stored as a separate stack. Encrypted string distinct from the static C2 configuration blob. Remus also introduces 2 additional anti-analysis checks executed before any C2 connection attempt. The first is sandbox DLL detection, traversal of the process environment block's in-load order module list, CRC32 hashing of each module name, against 11 pre-computed hashes corresponding to known sandbox DLLs, including snxhk.dll for the Avast sandbox, sbieDLL.dll for Sandboxy, cmdvrt32.dll, and cmdvrt64.dll for the Komodo sandbox, and others. The second is honeypot PST detection. The malware enumerates PST files under the Outlook files user profile path and checks for the presence of honey at bot.com.pst as a sandbox environment indicator. If either check fails, the binary terminates silently via exit process 0, leaving no behavioral trace. The MITRE attack coverage for Remus spans 8 techniques: T1555.003 for credential theft from web browsers via the Chromium ABE bypass, T1115 for clipboard data exfiltration, T1071.001 for C, to communication via ether hiding, JSON-RPC, T1055 for process injection via NT, create thread X, T1497.001 for virtualization and sandbox evasion, T1027.002 for software packing, and obfuscation, T1134.001 for system token impersonation as an alternative, ABE bypass method, and T1140 for runtime, C2 configuration decryption via ChaCha20 from the read-only data section. In terms of detection and response priorities, several actions are immediately actionable. On the network side, block all known C2 IPs and domains from the published IOC set. The list includes direct IPs on ports 80 and non-standard ports, as well as 30 plus C2 domains across .biz, .pix, .live, .com, .online, and other TLDs. Monitor for and block JSON-RPC requests toward public Ethereum endpoints originating from workstations. This is anomalous behavior with a very low false positive rate in most enterprise environments and a direct indicator of Ether hiding activity. On the endpoint side, monitor for direct syscall usage, specifically the absence of standard Windows API call chains where they would normally be expected, combined with code injection attempts into Chrome, Edge, or Firefox processes. Monitor for hidden desktop creation via create desktop W combined with browser process launch, which is the fallback execution path when no browser is already running. For threat hunting, search for the ABE wildcard string and the 51-byte shellcode signature in memory scans. Audit N, tcreate thread EX calls from non-browser processes targeting browser processes. SOC Prime has published Remus-specific detection rules covering direct syscall usage, API hashing, and stealth execution artifacts. Upon confirmed compromise, the response protocol is standard for a credential stealer of this class: immediate host isolation, full memory dump and process tree capture, forensic analysis of injected browser processes, revoke all credentials stored in affected browsers, reset passwords, and invalidate active session tokens. The session cookie theft capability means that multi-factor authentication may have already been bypassed on any authenticated session active during the infection window. This needs to be treated as an authentication infrastructure incident, not just an endpoint incident. What to watch going forward? Remus is in active deployment with Lumma still running in parallel. The Ether hiding infrastructure shift is the most consequential operational change. It removes a key dependency on platform cooperation that has historically allowed Lumma's dead drop infrastructure to be disrupted. The Tensor transition builds confirm that the operators behind Lumma have the development capacity to sustain parallel code bases through periods of external pressure. Any organization that has historically relied on Steam or Telegram dead drop blocking as a Lumma detection signal should treat that control as deprecator. The indicator of compromise set published by Gen Threat Labs is the current best source for network-level blocking, and the SOC Prime rules are the most actionable starting point for endpoint detection. And that's it. This episode ends. I hope it will provide you with clear and useful information. Until then, we don't think, we patch. If you are a new listener, feel free to subscribe to the RadioCSIRT podcast. We are available in both English, Italian, Spanish, and French on Apple Podcasts, Amazon Music, YouTube, Deezer, and Spotify. All open source intelligence links used in this episode are available on RadioCSIRT.com. See you soon for a new episode. Take care. Goodbye.